Okay, for the last talk of the day, it's my pleasure to introduce Sebastien Picard from UBC, who's going to talk about topological transitions of Calabi-Yau threefolds.
Okay, well, thanks a lot for the organizers for the invitation. I'm really honored to have this opportunity to give this talk today. I never met Professor Kuranishi when I arrived at Columbia as a graduate student. He had already left to go to Japan, but the complex geometry seminar at Columbia had a huge influence on my education, and well, that was a Columbia tradition that started with Professor Kuranishi. So today, this talk is going to be about deformation of Calabi-Yau threefolds, a type of deformation under which the Hodge numbers will be altered. So let's start with the setup. So we'll take Y to be a Kahler Calabi-Yau threefold. So we're going to be working in complex dimension 3, compact complex manifold. Y has trivial canonical bundles, so it has a holomorphic volume form we'll call capital omega. And by Yau's theorem, can be equipped with Kahler-Ricci flat metric we'll call little omega. And we'll further make the assumption that Y is a simply connected threefold. So we want to try to understand the parameter space of all these objects, and they're parameterized by two parameters in the Hodge diamond. There is the H11, that's the Kahler moduli, and there's the H21, which is complex moduli. And as we all know, there are many different Hodge diamonds which can appear. We want to try to understand this parameter space. So if we imagine ourselves as say theoretical physicists that would like to use these spaces to model something about the universe, the question is, right, we have all these different threefolds with these different parameters. Which one do we choose? What's the best Calabi-Yau threefold out of all these? And well, there's no such mechanism in physics to decide which one to choose. It's in fact maybe one of the common criticisms of string theory. But instead, one program to address this was proposed by Candelas, Green, and Hodge. And their proposal is it shouldn't matter which one you take, right? You should, in the whole landscape of Calabi-Yau threefolds, you should be able to start anywhere. And then there should be a process by which you can travel in this parameter space from one to the other. There should be a tunneling mechanism. So you start on one part of the landscape and you can travel to another. And by altering the Hodge numbers and throughout this process, there should be a unifying set of equations describing the physics. This was inspired by work by algebraic geometers, starting with Hilsenbruch and then further developed by Clemens and Reid and Friedman. And very broadly, this process for moving between threefolds with different Hodge numbers has two parts. The first part is a holomorphic contraction. So you fix complex structure and you send a holomorphic cycle to 0. This gives you complex singular space. And the second step is to now deform the complex structure and smooth it out. So to be concrete, we're going to be focusing our attention on the Conifold transition. So how does this work? We start with Y, and now in Y we look for -1, curves. So these are P1s, and they're embedded in such a way that their normal bundle has it's P1 sitting inside of a threefold. So normal bundle has two complex directions, and they're both O-1 and O-1 for the two normal directions. So said another way, there's a neighborhood of this P1, which looks like, or biholomorphically identified with a neighborhood of the 0 section and the total space of O-1 plus O-1 over P1, and that 0 section carves out the -1, curve. So once these curves have been found, can contract them to a point, and a change of variable shows that Sending this to a point is biholomorphic to this particular singularity here, which is the sum of the zi's is equal to 0. It's this particular kind of singularity that you see. And then the next step is to resolve the singularity in a different way, which is not this small resolution kind of way that we went in this direction, but rather resolve it in a different way by changing the complex structure to smooth out the singular space. So locally, it's very easy. If you sum of the ci squared is equal to 0, you can smooth it out by putting a t on the right-hand side. But then the question is, you want to attain this globally in such a way that when you look locally, you see that particular smoothing. And that's where this global condition comes in, which is Friedman's condition, which is that these curves that you contract should not be homologically linearly independent. They should be homologically linearly dependent, right? There should be a relation between the curves. And provided this, right, so Friedman proved that such a global smoothing does exist. Well, there's also work here by Kawamata and Tian to realize the higher order smoothing, not just the first order smoothing. So for our purposes, we can take this kind of as an existence theorem for the existence of a transition like this. You just need to start with your threefold y. You look for -1, -1 curves with their initial configuration satisfying this condition, something that can be checked easily. And then you're guaranteed the existence of a transition like this. So let's look at what happens to the topology of our space when we do something like this. So this is a classic picture in the physics literature, but this is just a local picture. This is just if we zoom in at the nodes where the singularities are and take a look at topologically what's going on. We start at the bottom right there with the arrow, small resolution. We're going to go backwards through that arrow in the small resolution in the previous picture. So topologically, that -1, -1 curve is the S2. So all we're doing is topologically sending the S2 to a point. We get a singular space, which is that cone there. And the deformation process, topologically, it just has the effect of switching the S2 for an S3. S3 appears on the other side. So this is just the local picture for the conifold, but now globally on our compact manifold, we may have relations between the homology cycles. So there's some global effects there, but roughly what happens is since you're removing S2s, your second Betti number is decreasing, and then you're introducing S3s, so your third Betti number is increasing. So more precisely, the formula is this. It's this n equals k plus c formula. So n is the number of nodes or number of initial curves. Start with n curves, and then if there are k linearly independent, homologically linearly independent curves in your collection of curves, that's the amount by which you drop your second Betti number, and then your third Betti number increases to compensate by 2c. So this process changes the topology, and it is a way to move between one Calabi-Yau to another while changing the Hodge diamond, Hodge numbers. But so here's the starting observation of our talk today by Friedman and Reid. So, well, as we see, as we just discussed, for sending 2 cycles to points, we could potentially be killing the second homology, right? So, for example, if the holomorphic curves generate the H2, you contract them, there's no more H2. So you do this process, and the object that appears on the other side no longer has any H2. And this is not a crazy thing to do. Very simple examples in the survey paper of Friedman are shown. I mean, you could just take Y to be just a quintic threefold. H2 just has generated by just rank 1. So you do this, it's going to drop, it drops to 0. And this process has created something which could never be Kahler, because as we know, a Kahler manifold has H2. Nevertheless, the complex manifold that comes up on the other side does have a trivial canonical bundle, so it could still be called Calabi-Yau, but it could never admit Kahler metric. So we set out to understand Kahler threefolds, right? And now we're forced to face the non-Kahler reality, right? This operation does not preserve the Kahler condition. And if we want to understand it, we need a formalism or framework which is more flexible, which also includes non-Kahler manifolds. So these could be, right, so these are some kind of non-Kahler Calabi-Yau manifold. They're complex manifolds with trivial canonical bundle, but still they are not just an arbitrary non-Kahler manifold with trivial canonical bundle. They're the ones that are connected to the Kahler ones through this conifold transition. So we hope that they would inherit some extra structure from that. So here are our big guiding questions, right? So we want to understand this from a point of view of differential geometry. We lose the Kahler condition, right? But what geometric structures are preserved? And how do our geometric objects vary as we go through? If we think of it as geometric objects representing physical quantities, and we want to understand the physics as we go through, should it somehow vary continuously, despite the fact that this transformation is, well, at least very discontinuous at the level of Hodge numbers. So that's our goal. So we would like to find a uniform, we would like to uniformize this from the point of view of geometry. We want the same uniform geometry, unifying set of equations. We go through a conifold transition, Kahler, non-Kahler, doesn't matter. We want to use the same set of equations to understand these spaces. So one example of how these non-Kahler spaces that are connected in this web of threefolds, they do inherit some extra structure. And one example is Friedman's DD bar lemma, right? So Friedman proved that although non-Kahler, these threefolds which emerge out of conifold transitions, they do at least still satisfy the DD bar lemma, despite not necessarily admitting a Kahler metric. And so, yeah, our question is from the point of view of objects in differential geometry, say metrics, etc. What's the unifying picture here? What can we use to study all these objects? So let's start by just looking at the local picture. So if we look near the nodes, right, what do we see? So yeah, the nodal singularity just looks like this V0. And this has a completely explicit Kahler-Ritchie flat cone metric. There's just the right power of the modulus of Z that you can take. You take the cone metric IDD bar R squared. And that power there just comes from solving the right ODE to get this to be a Ritchie flat. So it's a Ritchie flat cone. And in fact, there's a whole family of them as now you introduce the deformation parameter. So this is a candela stylosa. By putting in a radial ansatz, by looking for solutions which are just dependent on this parameter R. This gives an ODE. Ritchie flat condition gives an ODE. And they have a whole family of equations of Kahler-Ritchie flat metrics. And this is kind of accepted as the model geometry that we want to see when we look from the point of view of Kahler-Ritchie flat metrics, what we want to see when we look at these non-compact spaces. But of course, this is just the local picture. We're going to be seeing a neighborhood of this within a broader compact space. And so what's the program or Yau's conjecture in this broader setup? So we all agree in the Kahler case, the best metric would be a Kahler-Ritchie flat metric. But here now we no longer have necessarily a Kahler metric on the other side. So instead, the program is to replace this with a pair of metrics. And together, these should kind of encode some of the information of what is a single Kahler-Ritchie flat metric. So by that, I mean, in the case where these two metrics agree, we should recover the Kahler-Ritchie flat condition. But more generally, and if it happens to be a non-Kahler transition, then maybe these would decouple into two separate metrics on the tangent bundle. But nevertheless, we would like to see that classic model geometry. When we zoom into the nodes, we would like to see what we all agree is the best metric, which is the Candela-Stolosa family of metrics. We still want to see that where it could appear. And the non-Kahler-ness would come out further out in like the non-compact region. And so what equations, where would we get our set of equations for this pair? And this would be inspired by string theory, specifically a system of equations from heterotic string theory. So the first set of equations is what's called the balanced condition. So Fuli and Yau, they prove that although through the transition, you may not preserve the Kahler condition, but you can always find a metric whose square is closed. D omega is no longer closed, but now D omega squared is closed. And this was a special kind of Hermitian metric, which was studied by Michelson in the 80s. And Fuli Yau showed that these do exist through Conifold transitions. And they were inspired to look for this because this condition also arises in supersymmetry. It's a condition, so Strominger derived, starting from equations from supersymmetry, derived some non-Kahler constraints on a manifold, and Li Yau recognized this as this balance condition here. And so one way to interpret this Fuli Yau result is that though you lose the Kahler property as you go through, supersymmetry is preserved. This transition preserves supersymmetry, as this is an equation from supersymmetry, which can be shown to hold through the transition. And well, since then, this non-Kahler Calabi-Yau theory has been very active in the literature, studying triples where still have a holomorphic volume form, but the Hermitian form is not closed. Rather, it solves this balance condition. Sometimes it's also taken as this conformally balanced condition with this conformal factor. You can go between one or the other by making a conformal change of the metric, so we won't worry too much about this. And I just want to highlight, one area of research here is to explore this kind of non-Kahler geometry together with Teng Fei and Professor Fong and Shangwen Zhang. We developed a geometric flow. We have a program for exploring this non-Kahler geometry by means of this geometric flow. Here, the psi is very flexible. It can be chosen depending on the situation. There's some situations where you may want to take it to be a Poincare dual to certain special submanifolds. We also explored taking it to be these alpha prime curvature squared corrections from the anomaly cancellation equation. But nonetheless, anyways, this family of geometric flow is one way to kind of probe this non-Kahler geometry. Though it's not obvious by the way it's written there, it is can be written as a type of Ricci flow with some non-Kahler corrections there. But let's return to the Fuli Yau metric and give an idea of the construction of this balanced metric through Conifold transitions. So how did they do it? So so there's two steps in the Conifold transition. First one, you send the curves to 0. Second one, you vary the complex structure. So the first one, contraction of the holomorphic curve. And they write down their metric by gluing at the level of squares. So, okay, gluing what? So near the singularities, you have this Candela-Stolosa explicit model metric. And away from the singularities, they keep the initial Calabi-Yau metric. And it's just about matching these two up together in a way that maintains positivity. And the way to match them is at the level of squares. You don't match the omega with the omega. You go at the level of squares, because both of these in the neighborhood of the curves, they both look like dd bar of something. And so you can, behind the dd bar, you can place a cutoff function. And then you use this parameter R, capital R, to get positivity of this kind of matching of these two metrics together. So the first step, Fuli Yau, they produce a balanced metric on the singular space with singularities near the nodes, which are exactly the Candela-Stolosa model metric. And then the second step is the deformation of the complex structure. So here, right near the nodes, we have this explicit model by Candela-Stolosa solving that explicit ODE. So we just put that back. And then away from the nodes, right? We have this problem where we had our original metric. Now the complex structure starts moving, right? So now our metric starts picking up. It no longer stays a 1-1 form, right? It starts picking up components and other components. So we just take the 2-2 part of the square, but by doing that we lose the closedness. So since we lose the closedness, we have to add a correction term so that we take the 2-2 part of the square, add a correction term so it stays closed. But then you add a correction term, you may lose positivity. So then the key estimate in Fouliau is to show that that correction term actually goes to 0 in suitable norms as t goes to 0, so you maintain the positivity. So this is kind of an analog of, I guess, of Kodaira's theorem, right? Of if the central fiber is Kahler, then for nearby fibers, you still have a Kahler metric. Similar in spirit, right? But here it's not Kahler. We're talking at the level of squares. And also we have singularities, but it's kind of inspired by the same similar philosophy here. So our theorem, so that was the first, that's the first metric, right? So part of the program we're looking for a pair of metrics. We're trying to capture more of the information of a Kahler-Ritchie flat metric, and just a single metric satisfying this balance condition, that's not rich enough of a structure. We need more structure. And so the second metric here has to capture more structure. And in fact, it solves the Yang-Mills equation. So this is joint work with Tristan Collins and Professor Yau. And we solve the Yang-Mills equation through this conifold transition. And well, what's the gauge bundle? We take the gauge bundle to be the tangent bundle. So more precisely, we go through the conifold transition. Yang-Mills equation has to be with respect to some polarization or background Kahler form, or background, in this case, or non-Kahler Hermitian form. And so we take that form to be the Fouliau metric, and we construct a Hermitian Yang-Mills metric with respect to that Fouliau geometry. So another way to interpret this is, right, so as we know, Yau's theorem, one consequence of it is that the tangent bundle is stable. And so this is kind of a non-Kahler version of this result, right? Even though we're entering non-Kahler territory, the tangent bundle still remains stable. So this is another example of kind of these threefolds at the boundary here of this procedure, conifold transitions. Though they lose the Kahler property, they still retain some structure, and they still have stable tangent bundle. So no matter where you are in the landscape of threefolds, you may be non-Kahler, but stability of the tangent bundle is preserved. So this is just another way to write these equations. Right, so we now have a pair of metrics, the Fouliau metrics, the square is closed, and we also solve the Yang-Mills equation. So this is indeed a generalization of Kahler-Ritchie flat metrics, right? If we take a Kahler-Ritchie flat metric, no need to take two metrics, just take both to be the same one. Of course, you have the closeness condition, and then, well, the Ritchie flat is like Yang-Mills with respect to itself, so that is satisfied, but when it splits into a pair, you have a decoupling, where now the metric G taking the trace is not the same as the metric H, where the curvature is calculated. There's also related work here by Schwann, who solved the Yang-Mills equation, but not on the tangent bundle. They needed an extra technical constraint, which was that it only worked for bundles that are holomorphically trivial in the neighborhood of the contracted curves. And well, the neighborhood of the curves is where all the action is happening. So we wanted to remove this assumption that the tangent bundle does not satisfy this assumption. And there's also other work by topologists or algebraic geometers studying maybe stability, but not from the metric point of view, maybe from the stability point of view. And Buskov is able to obtain stability in the case. So there are some examples where this transition produces a connect sum of a bunch of S3s cross S3s. And in that case, Buskov, using algebraic and topological methods, proves the stability of the tangent bundle. But as a differential geometer, I'm really interested in the metric. I want to see what the metric looks like. And this is another consequence of our work, is that we have a good understanding of what this metric looks like near the nodes, right? So we had this local picture candela stylosa. And what we proved is that in this global non-Kahler setting, despite that, when you look in locally near the nodes, you still see this candela stylosa picture. So the two metrics do split into two, or this non-Kahler geometry is represented by a pair now, but both of these metrics are close to the one candela stylosa Kahler-Ritchie flat metric near the node. So here we have these decay estimates. If you're not familiar with this scaling property, you can just take k to be 0, lambda is positive, and you have this kind of decay of the two metrics are close to this explicit ODE model. So let me outline a few steps of the proof. 2 steps, right? First step is the generation of the curves, right? So here's the setup. So this Fouliau construction, in fact, it does give a sequence of balanced metrics on the initial threefold, and in that sequence, it's sending the area of this holomorphic curve to 0. And with respect to these non-degenerate metrics, we can appeal to the Donaldson-Uhlenbeck-Yau theorem. It's the non-Kahler version of it. So technically, there's some modifications to the non-Kahler version due to Li and Yau. But anyway, so we can get by the Donaldson-Uhlenbeck-Yau theorem, for each of these metrics here, we get Hermitian-Yang-Mills metric. And the question is to extract a sequence. So we have a sequence of Yang-Mills metric with respect to a background, and the background is degenerating. It's sending the area of the curve to 0. And now we want uniform estimates along the sequence so that we're able to extract a subsequence, right? So that's the plan. So it's a study of Hermitian-Yang-Mills equation with degenerating background metrics. So that's the strategy. And so to do this, right, we need to obtain uniform estimates, right? Uniform along this sequence so that we can use our Zela-Ascoli on compact sets and extract our limit. So there's 2 metrics, the Fouliau metrics, that's all very explicit. We have a sequence that converges to this singular balanced metric, which I described earlier. But then we also have this sequence of maybe more mysterious Yang-Mills metrics along here, and this is what we want. We need to estimate the HAs in a uniform way. So we're developing singularities along these curves, right? So these background Fouliau metrics GA, they're sending the area of the curves to 0. But away from the curves, everything's smooth. So any estimate which can be localized is all good. If there's any estimate in this Yang-Mills theory which can be localized, then we can just apply those local estimates away from the singular curves, and we're in business. But the first estimate that cannot be localized, right, is the C0 estimate for HA. This is the Uhlenbeck-Yau estimate, or this is how we approach it. So this C0 estimate involves a stability condition, a global condition on the bundle. So following this Uhlenbeck-Yau technique, it's a proof by contradiction. So we have this sequence HA, and suppose the C0 norm is not bounded along the sequence as A tends to 0. And then by rescaling and following these Uhlenbeck-Yau estimates, we can see a convergent subsequence of the rescaled HAs, which produces a destabilizing subsheaf. And we use that to violate the stability condition. And it's the subtlety is the difference with Uhlenbeck-Yau is here, the limit is going to be a singular manifold. It's going to have these nodal singularities. And we know that the original threefold is stable, not the nodal one. So we have to, take care of that point. But that's the main difference. After that, in fact, the estimates do localize. So the next estimate is a C1 estimate. And here we follow the style of an estimate from Monge-Ampère equations from Fong, Sessom, Sturm. It goes back to this Calabi C3 estimate, but in the formalism of Fong, Sessom, Sturm, You can see how this sort of estimate would apply for the Yang-Mills equation. And it applies very well even with putting a cutoff function inside the estimate, still works very well. And so that's the technique we use to obtain the C1 estimate. And then for Yang-Mills, once you have the C1, there's a standard elliptic PD theory to give the higher order local estimates. So then away from the curves, you can take your limit. And the final step is trying to recognize what we see in the limits. We want to have some kind of local uniqueness where now when we look into the nodes, we want to see that model geometry, right? We want to see that Candelas-de model metric, and that's the next step in the proof, is to prove polynomial decay of this metric towards this, the limiting unknown metric towards the model Candelas-de metric. And this is proved using Mori type estimates. Okay, so that's the first step, curves degenerated. We get our singular Yang-Mills metric. Second step, now the complex structure is going to start moving, right? And we want to perturb our singular metric to smooth Hermitian Yang-Mills metrics. And this is done via gluing technique. So right, this technique in geometry going back to Taubes in the 80s, and has been since used with great success by many differential geometers in all areas, and here we use it as well, right? So we have a Yang-Mills metric with cone singularities, and we want to desingularize it by gluing in this model that we have, and this Candelas-de model. And well, you do the gluing with cutoff functions, you try to match them up, you get an approximate solution. It's not a perfect solution. And then you have to use implicit function theorem to perturb it to get a genuine metric. So this is second step of the proof involves gluing and desingularization techniques. So that's the outline of the proof. Okay, so I guess if there are no questions, we'll go back to the big picture here. I just want to reformulate the equations in just a slightly different way, maybe inspired from the point of view of physics. So in physics, some of the fields that appear, there's a F, which is a two-form field strength, and that we all know as the curvature of the Yang-Mills connection. That's the same F as before. But in string theory, there's also a three-form field strength. And Strominger proved that in this context here, the three-form field strength is d minus d bar of the Hermitian metric. So we see in the Kahler case, there's no three-form field strength, but in the non-Kahler case, this is a non-zero field, and the equations can just be recast in this way. So the first equation is the Yang-Mills equation that we solved together with Tristan and Yau. And the second equation for H is just a reformulation of the Fuli-Yau metric of the balanced. The balanced equation can be manipulated to be rewritten in this way here. But in this way kind of puts the fields in the forefront, right, of the equations. And we see that right, we can maybe interpret this result as some kind of polystability or stability of the tangent bundle, but instead of just involving a two-form, there's also a three-form field strength in there as well. So, and this is what we mean by, right, so we can interpret this as, right, in the this threefold landscape, we always have a sort of stability of the tangent bundle, despite losing the Kahler. There's one more equation, which is also predicted by string theory. This is the anomaly cancellation equation. This equation still remains to be solved through conifold transitions. And right, we hope that with all these full equations, this system kind of hope would recapture some of the richness of Kahler-Ritchie flat metrics. We don't have Kahler-Ritchie flat metrics, right? But this system of equations should give us still some nice geometric properties, and that's what we hope to use to uniformize and study this space of Calabi-Yau threefolds. Okay, so no questions about that. Otherwise, I'll move on to another topic. Again, we're inspired by equations from supersymmetry. And there are supersymmetric equations which also single out special submanifolds. And the motivating question here is, what are some of the special submanifolds in this context? We have Conifold transition produces this Fouliau geometry. We've got a holomorphic volume form, got a balanced metric. What are special submanifolds, right, in this setup? And so a natural functional to consider is this integral, this conformally changed area integral. So perhaps we're more used to the Kahler Calabi-Yau setting where the norm of the holomorphic volume form is constant. So this is just the area functional of a submanifold. But in non-Kahler geometry, this norm starts fluctuating. It's not necessarily constant. And so we want to put this into the functional and look for extremum or extremizers of this functional in a given cohomology class. So we take a cohomology class in H3, and we want to find the special cycles which extremize, which minimize this functional. And so this question was developed in the paper of Harvey and Lawson. There's a section in Harvey Lawson's paper which does discuss non-Kahler Calabi-Yau, right? So they do discuss this functional and discuss how their work implies that minimizing this functional can be written in this very simple and elegant equation. We all know the special Lagrangian equation here, which is equivalent to finding the extreme points, right, of this function. So these are the special 3 cycles that we're going to be interested in, right? We're going to be interested in special 3 cycles in this non-Kahler geometry, which are extremizing this functional, and we still call them special Lagrangian, just like in the Kahler case. It's the same equations. There's another point of view to arrive here from supersymmetry and equations on spinors, right? So the way physicists would arrive here was quite different than the way that Harvey and Lawson arrived at the same place. So for a physicist, these equations first look like constraints on spinors. So you have eta to be a positive chirality spinor, and those equations there are the ones which are produced from supersymmetric constraints. And then the question is, what kind of structure does the existence of such a spinor imply on the geometry of the space? And so this was a question explored by Strominger, who proved, so the first work where h is 0 and phi is constant. This was Candelas, Horowitz, Strominger, Witten, which obtained the Kahler Calabi-Yau structure and then generalized to allow non-constant phi and non-zero h. And so Strominger proved that this kind of condition on spinors, it equips your manifold with a complex structure, integrable complex structure, holomorphic volume form, and then balanced metric, right, as we discussed, was also interpreted by Li and Yao. But since we're talking about special cycles here, I want to point out this calculation of Becker-Strominger, which is in this context. And inspired by another equation from supersymmetry, they found this identity here, which recovers Harvey and Lawson's result. So there's this equation from supersymmetry, this P of eta, and it doesn't matter for now explicitly what it is, but they expanding the square of this quantity produces 2 terms. One, which is this topological charge on the left-hand side here. And the other term, press the button. I did press the button. Well, oh, never mind. I just noticed that, so there's an error message on this TV, but I see that it's not up on the blackboard, so we'll just ignore it. So anyways, right, so expanding the square here gives on one hand topological charge on the left. It gives that functional we're trying to extremize. And so we see exactly that to extremize, because if we look inside the fixed class, right, that charge on the left is not going to vary. And so we see that exactly we find the absolute minimum of this functional is equivalent to just this square quantity vanishing and unraveling. And so what Becker and Becker-Strominger did is unravel that condition constraint, and they found the same equations as Harvey and Lawson, the special Lagrangian equations here. So it's another kind of spinner point of view of arriving at these special Lagrangian cycles, and even in the non-Kahler case, this is a very natural set of constraints. So our next theorem is right. So we want to understand special submanifolds through these transitions, and so our next result, this is joint with Tristan Collins, Sergei Gukov, and S T Yau, and our result is that we construct special Lagrangian three spheres on the other side of this transition. So we have this global non-Kahler geometry, that's this Foulier geometry, and the conifold transition, as we discussed, it kind of switches a two-sphere and introduces new three spheres. And we showed that these three spheres can be perturbed to special Lagrangians with respect to this global non-Kahler geometry. So in fact, there's a sequence of metrics on either side of the transition, right? So the first sequence of Foulier metrics, they're the ones that are all balanced. They're sending the volume of the holomorphic curves to 0. And then comes out on the other side, comes out these special Lagrangian three spheres, right, with this other sequence of metrics on the other side. And so this kind of gives like a metric interpretation of this topological picture we had earlier, just local topological picture of two spheres and three spheres. Here it's realized in kind of a global non-Kahler geometry setup. And it's another instance that we can interpret this as some kind of supersymmetry being preserved. So I gave this argument here for three cycles. There's this similar argument as well for two cycles, which singles out the special two cycles from supersymmetric equations to be holomorphic curves. And so what this result is saying is, yes, we are losing supersymmetric two cycles. We're losing these holomorphic curves through the transition, but we are reintroducing special Lagrangian three cycles on the other side. The supersymmetric cycle condition is being preserved, although it's changing from a two cycle to a three cycle. Right, so this is what I was saying, right? We upgrade our topological picture, our very basic picture that at the level of topology, we're exchanging two spheres for three spheres. This is being upgraded to non-Kahler global complex geometry. And instead, with our additional structure that we have, we're exchanging holomorphic two cycles with special Lagrangian three cycles, all with respect to this global non-Kahler complex geometry and these metrics satisfying these equations from supersymmetry. It's the last talk of the day. We're going to end early. Thanks for your attention, and thank you very much.
Are there any questions?
Yeah.
So you proved that the Hermitian-Yang-Mills equation on the tangent bundle survives the Conifold transition, and also you construct this special Lagrangian cycles, smoothing out. So the special Lagrangian cycles also pass out, like survives. That would get some solution.
Oh yeah, no, we haven't looked at that. Yeah. Oh wait, no. On which side of? Well, can you repeat? Yeah, we're deformed Hermitian-Yang-Mills. So how would that come in?
I guess morally, it's special Lagrangian. Equal to the.
I see. Oh yeah, no, this is right. Yeah, this is certainly an interesting future direction of research. Is right. Is understanding the interaction of this with mirror symmetry. Right. So you would do mirror symmetry on both sides of the transition. This would give you two mirrors, right? And you'd want to know how, like, does the how does a transition, first of all, interact with mirror symmetry? You go to the mirror, you do the transit, because you can also do a reverse transition, is the thing. So you can write, go the reverse, instead of degenerating the curves, you degenerate the special Lagrangian cycles and go the other way. And then you could ask, yeah, if this is a commutative picture, and then as you suggested, right, what would be the corresponding objects, right, when you do the mirror symmetry? I think this is a great question. Hopefully we can explore in the future, but yeah, it's a very, very good point. Yeah.
Any other questions?
What numbers the only invariants which are changing, or do you have other numbers?
Oh yeah, no, those are the only ones I'm aware of. I would love to, yeah, talk to someone who knows more about, right, like Gromov Witten theory or Donaldson Thomas, and see what's happening from that point of view. Yeah, I'd love to know more about that. Yeah, definitely. Specific, or it'd be even more interesting if something were preserved, if there were some number, some invariant, right, that would go through unchanged. That would be very interesting, because, well, the Hodge numbers are jumping, so.
Okay, I'll ask a question. What about more general transitions?
Yeah, we we don't know anything about those yet, but yeah, that's a good point, right? So there's I think we'll hear about this tomorrow, right, in Professor Friedman's lecture. Right, so we focused on the one example of transitions changing the Hodge numbers, which is contracting the -1, curves. There's other ways too, right? There's ways contracting divisors or other curves which are not -1, curves. And there, I mean, it's I think, as far as I know, everything is very open. And there's a lot of room to explore there. I think very, very little is known.
Okay, if there are no more questions, let's thank Sebastien again.